Right. Like, for example, well, we'll talk about that later. Where were we? Airplanes? Submarines?
Airplanes.
Oh, yeah, submarines. Yes, submarines. So, like, if you're in a submarine, right, and you go down below, then what happens to the side of the submarine?
It goes down.
It's smaller. It actually compresses a little bit. And as they come up, they expand a little bit. And so, when you make a submarine or airplane, you kind of have to adjust for that and make it somewhat flexible. Otherwise, it'll break. Yep.
Well, that's why depth charges work against submarines, because they create a region of high pressure which moves into the submarine and, like, compresses the submarine.
And that goes to page 395, Pascal's Principle. So, Pascal's Principle states that essentially within a fluid, pressure exerted equally in all directions. So when you're talking about fluids, they're not very compressible overall. Some are more compressible than others, but generally they're fairly non-compressible. And if you apply a force in a direction, it's going to hit the next molecule, hit the next molecule, hit the next molecule, but it also pushes in all directions. So if you have a closed container like this, and you apply a force on one part of the container, that force is going to be applied equally in all directions. And that's what happens with the Cartesian diverter. So what you do is, not only am I pressing to the sides, but that force is distributed equally in all directions, including up. So it forces water up into the air pocket, which then decreases the density of the little eyedropper. And as the density decreases, it falls and sinks.
You can see the air compressing.
And you can see actually the air compressing right there. So it's now about half filled with water, and there was not very filled with water at all. Play with that around. So that's Pascal's principle. Same idea with the depth charge. The depth charge comes in, and it's just this size, right? And then it explodes and creates a whole bunch of gas. And now instead of being this size, it's this size. Well, where does all that water go? It's pushed out with this force. And since it's applied equally in all directions, if that force is being pushed everywhere, if you happen to be within a certain radius before that force dissipates due to friction, then you're going to find you get a big push. If you can't withstand the big push, then you'll be destroyed. Yep.
So, if you actually get a direct hit, like it only has the top of the submarine, it stays there for a while and explodes the whole top.
You can be pushed in.
Essentially,
Yeah.
And then they all drown and die, and everybody's happy.
Yeah. So, okay. So your book on 395 talks about hydraulics. And that's always a nice one. Because what they do is essentially they use Pascal's principle and they fill it with this fluid, right? And so they take a small thing and they apply it to a big thing. Okay? And if this is all filled with fluid, then you can use a small force, and that force is going to be distributed over a large area. So what that means is you can take a mouse, let's say. Let's see, that's a mouse. It's a mouse, you can't see it. And he can push around. Let's go with my friend, the elephant. Right? So, is that better?
That looks like a fat mouse.
Yeah.
Okay, it kind of looks like that. Fine. Skinny mouse, fat mouse, mouse, elephant. He can push around an elephant. So as he pushes down, that force is distributed, and all throughout that, he can push the elephant up. Now, what is the mouse sacrificing in this case?
Himself.
Distance. He's sacrificing distance. Oops. So, let me show you here. So, okay. We got a big piston, little piston. In between you have a fluid, right? So, we got a big piston pushing a small piston. You push down a little bit. Little piston goes up a lot. I got to fill this with fluid again. Let's get some air there. You take the little piston, push down a lot. The big piston goes up a little. So, you have the force equally distributed through the fluid, and now it's going over a larger area, so you can use a small thing to move a big thing. That's how the hydraulics and brake systems work in your car. You take this little brake pedal, you push on it, and it goes through the fluid, and it's applied to your brakes.
That's what brake fluid is.
Yeah, that's what brake fluid is for. So that's just Pascal's principle. Works pretty well. And that's also Pascal's principle. All right, let's go on to 396, Bernoulli's Principle. Bernoulli's Principle is a weird one. So, Bernoulli's Principle. So, Bernoulli Principle, his idea was that a fluid that's moving has lower pressure within the fluid. So, within the fluid, there's lower pressure. And now, this gets interesting only because I mentioned before, pressure always goes from high to low. Don't forget that. That is important for the whole chapter. So I guess there's 4 ideas. There's 3 ideas. 3 main ones the book says. Pascal's Principle, Bernoulli's Principle, Archimedes' Principle, which we'll get to later. But this idea that pressure goes from high to low is very important because, okay, let's say you have a moving fluid, right? So Bernoulli says, well, within the moving fluid, this is a lower pressure, which means that the pressure around it is higher. So it goes from high to low, so it's pushing in this way. Some people say that, and I think your book mentions this, if you have that happy little plane, and let's say they assume that air goes over the airplane, and since it has a longer way to go over the top of the airplane, it's going faster. Since it's going faster, there's a lower pressure here, which means it's higher under here, giving the plane lift.
Aerodynamics.
Okay, so my question is, how do planes fly upside down then?
Because they have thrusters.
Because it doesn't really matter.
Because planes actually get most of their lift because they are tilted towards the ground. So this is the plane relative to the ground, and sure enough, as the air comes in, what is the plane doing to the air?
It's pushing off.
It's pushing it down. And action-reaction, what's the air doing? It's pushing it up. So if you're going fast enough, with the wings tilted enough, you get enough thrust.
But if you're going upside down like that, then your plane just falls.
If you're going upside down, you can't go straight upside down. You once again have to angle the wings. So you get enough push.
So if you go like that, wouldn't you just fall to the ground?
Yeah, that'd be bad. You stall. So, this may be true. It is not the primary way that airplanes get their lift. So they're going to get a little lift from Bernoulli's here, but most of their lift is getting because they're pushing the air molecules down, and the air is pushing them back up. Okay? Spray bottles work by Bernoulli's Principle. Chimneys. Here's one for chimneys. So you got this happy little fireplace, right, with crackling fire. And we need a little red here for the fire. And so so at the top, you have all the smoke coming out, right?
It's a meeting plane.
Right?
It's hitting the plane and it's going to burn.
Yeah. So let's say we have a breeze coming by. Since we have a breeze, according to Bernoulli's Principle, is this high or low pressure?
It's going from high to low, so that's low.
It's low pressure.
It's low pressure. Since it's a moving fluid, this is low pressure. So where's the high pressure?
On the left.
On the inside. It's going to push the smoke out the chimney. What happens if it's reversed? What if in the house it's a lower pressure than out here?
All smoke go inside.
You're going to get a smoky house, okay? Now, of course, you also have the heat, which is hot air is less dense than cold air, so hopefully it'll rise up. But there may be a point where the high is greater than the low and push the smoke back in. So most of the time, chimneys work just fine. Sometimes they don't. It's not happened to me. There's one time that we forgot to open the flue, and then it was smoky. That was a problem. Okay, let's try another one. So, you have this happy little house, right? With happy little windows and happy doors. Okay. And most of the time, you've got things like, oh, I don't know, tornadoes coming by. Now, according to Bernoulli's Principle, in the center of this high winds, is it going to be high or low pressure? Yes?
Higher pressure on the inside and lower pressure on the outside because the outside is up, is moving faster, and the inside isn't really moving very much.
You got the right reason.
Got the right reason, but I messed up. So, it's very low pressure on the inside. Okay, because it's surrounded by all this swirling wind. According to Bernoulli's Principle, it's going to be low pressure. The winds themselves are generating a lot of high pressure. Now, let's say this low pressure zone goes over your house. What happens to your house? What's that?
It goes up.
It goes up. Now, let's say the foundation is really good. A different part of your house goes up.
The roof.
The roof. because inside is a higher pressure zone than that low pressure zone of the tornado, and so your roof pops on off. So it's very common during storms like hurricanes, tornadoes, for roofs to pop off.
Is that how the eye works in a hurricane?
Yeah, exactly. Welcome, welcome.
Louder than you.
Okay, so that's that. Okay, and then later on with buoyancy, but I want to show you a couple things.
What about
That's never good.
Okay,
Archimedes' principle?
so we'll do Archimedes' principle in a little bit.
Thanks.
Okay, so let's do this
Oh,
first.
we're doing
Okay, see, where should I put this?
Oh, no, I just had.
You put it right up here.
I just had.
All right, so you've done this before, right? You go to the
It's green
restaurant,
flavor.
you get something to drink, you're waiting for your food, and you mess around, and you do something like this.
Oh, I know this. Yes, I love doing
And you
that.
can make a caterpillar.
Yeah, so here's the question. Why does the water stay there? Why doesn't it just fall out? Normally, it just falls out, right? I mean, gravity works. It still works. How is all of a sudden, by putting your finger on top, you stop gravity?
Because the
So,
pressure.
Because there's no air coming in through the top, pushing down on it, so it's like a vacuum.
there we go. Well, how come it doesn't just fall out anyway? Why does having that vacuum make a
You have
difference?
to have something for the air to come in.
Yes?
Because there's air pressure outside it and it's pushing up.
Exactly. There's air pressure all around us. How come we don't feel it, Mr. Smith? Because we're used to it. Our bodies are adjusted to it. And sure enough, there is air pressure. Watch this. So watch this. There should be a drip or two coming out at the beginning. It's really close. And then it stops. Because as it comes out, a little bit at the beginning, it's creating lower pressure in the straw than outside of the straw. And like Millard says, it's pushing back up. That's how that's working. Now, how does the straw work in the first place? How do you get to suck up stuff? Yes. Exactly. You're making a low pressure inside the straw than outside the straw, so the push
Pushes down and then up.
pushes down, and it actually goes up the straw. Very nice. Okay, so let's try another one.
Is there a way you can get it all the way to the top of the straw?
Yeah, I think so.
If you
Yeah,
submerge the straw all the way.
Oh,
No, you just
if
suck
did
it in.
Yeah, you just stuck it in
Other than
really fast.
Oh.
Oh, yeah, I
You
do
suck
that.
it in.
Okay, you've done this before, right?
Oh, yeah.
Oh, got it. So we've got a thing full of water being held up by a little piece of paper. Why does the paper stay there? Yes.
Because the air pressure has more area to push up than the water pressure.
Air pressure is very strong. It's like 14 point something pounds per square inch. So this little bit of paper is getting pushed up by air pressure. You release it, and sure enough, gravity still works.
In DC? Wait. What was that thing where they put the paper on it and then they take it off and the water stays there?
Ah, so you could do it where, okay, so they do it with a screen, right? So they put a screen on top, and you have it upside down, they release the paper, and it's still there. Because the screen has plenty of surface area that is still being pushed up.
Oh,
Along with, you combine the screen with the surface area with the water tension, essentially, or hydrogen bonding tension, and it'll stay there. But if you pour it out sideways, it's not there. It'll fall out. That's a good one. I should do that one. Alright, here's another one. I should get some goggles for this one.
No, how about you burn off your eye?
Oh, no. I think
no, dude.
Ooh, I said exploding soda. I said exploding soda.
Ooh, explosions!
no.
Explosion!
Oh, we're doing this.
Mr. Shears, I said that you can't melt aluminum.
It's like my science fair. We're heating water.
Boom! Boom!
That
That doesn't want to lie.
Doesn't look like that, does it?
It's flawed. It actually
That was a tiny flame, that's why.
Oh.
It's like sparkling water.
Okay.
But you can mix it with like.
So,
That sounds like carbonated water. I hate sparkling water.
Yeah, but we can add stuff to it. Sparkling water tastes good if there's a little flavor.
So you guys have done this
Doesn't make
before,
the shape of
Yeah,
it.
for my science fair.
yeah.
For my experiment, you can't melt aluminum, Mr. Shears.
Is this something
I'm not trying to melt
Water.
Well, you can melt
So I put a little water in here. What I'm trying to do is fill this can with water vapor. Now, water vapor, which one takes up more volume?
Vapor.
Water vapor takes up like 600 times more volume. right? So a lot more volume. So I'm filling this with water vapor. Now what happens when I suddenly seal it off?
Boom.
It'll explode.
Yes.
It'll go back to water.
Okay.
No, it'll just
So the
keep
top can
going.
pop off, but right now the top is open. So this is open air. So water vapor, as you can see, is escaping out into the open air. Yes.
It'll go back to water.
It goes back to water. What happens when all of a sudden it goes back to water? All that volume is reduced. So what happens with pressure?
Pressure of the can.
What?
Pressure
Decrease.
Mr. Shoes allow 15 minutes.
So the pressure decreases, and we say that pressure goes from high to low, therefore pressure outside is greater than pressure
Mr.
inside.
Shoes, that's a really lazy way to pressure a can.
Oh yeah, let's see if it works. Oh yeah. Not a problem. So pressure goes from the high pressure, you and I are breathing this, to low pressure inside the can.
So last time is don't.
What is the water doing here? It's acting as a
Sealant.
sealant. Okay, let's try another one. I'm gonna need something else for this.
A person.
You know, some blood.
I need someone else.
Freeman, you're welcome.
No, not a person.
Freeman,
Get out.
Freeman, your pocket
Oh
watch.
no. It's
In
so
here,
fun.
pocket watch. 15 minutes.
No.
So stop it. So stop it.
That's what I was trying to say.
It doesn't matter.